All right, we'll go ahead and get started. I'm Dan Wright. I'm one of Aaron's many advisors. What, 3 advisors?
3 advisors.
3 advisors. And so thanks everybody for coming. So I want to say a few words and then I'll turn it over to Steve, yet another of Aaron's advisors, and then we'll get on with the main affair here. So, so just sort of a little bit of housekeeping stuff. So we'll have Aaron's research presentation. Unless you have just a very, very quick question of clarification, let's save all substantive questions for the end. At that point, ask very, very hard questions. And then, let's see, a couple of other things. So then the committee will enter closed session. And then what we're going to do is somewhere between 11:30 and 12 over in 1269 Engineering Hall, there will be a champagne toast. Anyone can come. that will be either to celebrate or to commiserate with Aaron, depending on the outcome. And let's see, I think that was all in terms of sort of announcements here. So, so just a real quick, a few words here. So myself, Steve, and Carolyn Boder, who's a third advisor and on the Ph.D. committee on Zoom, she's now at University of Delaware. Back in 2019, we were writing this research proposal that we were all really excited about. I'm not going to tell you what the proposal is about because you're going to see throughout the next 45 minutes or so. But as we were writing it, I kept thinking, well, I don't know what we're going to do if this proposal actually gets selected for funding and we actually have to do this research, because we need somebody who knows hydrology, we need somebody who knows atmospheric science, we need somebody who can run atmospheric models, and somebody who can code in Fortran. And that doesn't exist, that last point about Fortran, particularly in the, under 65 age category. And so then, it was only a couple weeks later after we got the favorable decision on that proposal that I got this email from this guy at UC Davis. Said he had, an undergraduate degree in physics and atmospheric science, a master's degree in civil environmental engineering with a focus in hydrology, and he was interested in coming here for a PhD. And so I wrote back, I was like, do you know Fortran? Fully expecting, that, well, if this guy comes, he could probably learn how, it turns out he did. And so I don't know how this came about. I don't know if it's some higher power or what, but here we are. We got the perfect person for the job. But the other thing that I wanted to just say is that beyond the really cool research and all the hard work that went into it that you're going to see here showcased today, Aaron has been a really positive voice in my research group, Steve's group, the broader water resources engineering group, and really, even further than that. Natural leader, community builder. You've done a lot, I think, to help other students, even faculty, and I really appreciate all you've done for that. So we'll leave it there. Oh, actually, no, I'm not going to leave it there. One last thing here was that yesterday it was announced that he won the College of Engineering's Mentoring Award for graduate students. Completely unsurprised by that, but it was very much deserved.
Great. Well, you covered most of things, so I'll just add maybe a couple more. First, I want to just thank everyone that's here and all the people online. This is probably about the hardest time of year to get a group of people here. We've had the semester, everyone's tired. There've been a whole bunch of people defending all the guest lectures that we invite from other campuses that we don't have come in January, February, kind of are crunched into the end. So the size of the crowd, I think, is a real testament to who Aaron is. And Aaron kind of builds a community wherever he goes. And there are people online, I'm sure, from AMS, where he's been really involved in the student leadership group. There's people from NCAR. He just went to AGU, or EGU, but he's also been active in AGU and the technical committee there. So I'm sure there's lots of people from all over the world here to see this presentation. And that's a testament to you, Aaron.
Thank you.
Second thing, I think that probably Dan already hit on is that he was at University of Nevada, Reno for atmospheric sciences, then Davis. Before that, where was he? He's from Elko, Nevada. And you might say, why would someone from Elko, Nevada want to study extreme precipitation and urbanization? Nevada is the driest state in the union. And the population of Elko County is 50,000 people, 17,000 square miles. There's an order of magnitude more people in Dane County and an order of magnitude less space in Dane County. So it's not a very urban place. I thought, well, maybe there's a hydrologic reason. I searched, and there was an extreme event, hydrologic event, flooding in Elko in 2017, so a couple of years before he came here. What do you think caused it? Oh my gosh, someone needs to answer. This is not looking good. You're not,
No,
if,
I know.
if,
Don't worry.
if
I've
the
got it.
hydrology group doesn't answer what causes flooding, this is gonna be a rough talk. Rain, yes, rain. How much rain? Half an inch. Half an inch of rain.
Yeah, it wasn't a lot of rain.
But there was snow, 5 inches of snow in the previous 2 months. And that's enough to cause flooding in Nevada. So I think that maybe if I search for a reason, you wanted to come to places where there were bigger problems, that you could more extreme rain and more urbanization.
Yes.
So I think I'll leave it there and turn it over to Aaron.
Awesome. All right. Thank you. Thank you so much. Okay. Welcome everyone to my dissertation defense. As we all know, key to a good defense is a good offense. So Dan and Steve, please come back up and defend your dissertations. Just kidding, just kidding.
I was going to say this should be easier for Aaron than almost anyone else, because it's kind of just like a Tuesday.
Yeah.
Where he has Dr. Voder, Dr. Wright, and I ask him how his week went.
So today we're going to be talking about my dissertation work, where we're going to be looking at the implications of adding in widespread urban greening on both ecohydrologic and hydrometeorologic processes in urban regions. I say urban regions, but we're really going to be honing in on Milwaukee, Wisconsin. So to start off, we live in urban areas. Shocking, I know. 50% of the world's population lives in urban areas. We're more urbanized in the United States, except for where I'm from, as we just heard. And by 2050, we're going to have a larger amount of the world's population increasing to be in these urban spaces. And that's not necessarily a bad thing, but it does start to mess with how hydrology and the atmosphere interplay with one another. So since the early 2600 BCE, we've had this idea of knowing that urbanization changes hydrology. We've had to add in rain gutters to be able to capture water in the Indus River Valley, in Mesopotamia, in ancient Egypt. And by 1833, we had our first idea of urban heat islands, which are basically the ideas of urban spaces are hotter than the surrounding rural locations. So you can have hotter areas inside spaces. And these kind of bring into consequence of urban spaces in general. So if we look at Milwaukee specifically, we can see that if we look at a study that was done in 2022 by colleagues Tang et al., that increases in flood depth are pretty correlated with increases of impervious surfaces, right? This is the downtown region of Milwaukee. We're going to be paying attention to that a lot throughout this presentation. There's a lot of pavements, there's a lot of buildings, and that has the highest flood depths. But as we move to more suburban areas that have more vegetation, there's less flood depth. And that's because we are able to infiltrate water or put water into the soil and reduce flooding. We also can look at maps of heat and urban heat. This is a study that was done by the National Center, or the Department of Energy, I believe, in Milwaukee 2 summers ago to map out the urban heat island during the daytime. And when we look at this, even though the scales are a little different, and these are like slightly different projections, we can see that there is a significantly high spatial correlation with places that have high flooding and high heat, right? So in this downtown region, we have a lot of heat, we have a lot of flooding. But we can also see the opposite. In locations that have a relatively cool urban heat signature, we have a reduced amount of flood inundation. This isn't the only thing that can happen though. So there can be unexpected interconnections between these urban hazards. So let's walk through. We have urbanization, and we've talked about flooding so far, and we've also have talked about heat. But the interplay between heat and the atmosphere and urbanization can cause rainfall enhancement itself, and then that rainfall enhancement can cause an increase in flooding. So we have this vicious cycle that occurs, where just because a city is placed in its location, we can have more rainfall, more flooding, and then we have this other heat factor that is all interplayed with one another. A critical part of my dissertation work is trying to understand some rainfall mechanisms, so I want to talk a little bit more about this urban rainfall enhancement in depth. So cities are able to enhance rainfall just by being present. And cities of most sizes, even probably Elko, Nevada, but you would need much, much more data than we have, years and years to be able to get a signal. So let's say that we have an air mass that's going to arrive from the west that, at least in this, talking about Milwaukee, most of the air masses are going to be arriving from the west. That's preferential for rainfall. So we're going to have rain anyway, or it's going to be just on the edge of either causing rain or not causing rain. As it starts to interact with the city, which is both hot and rough, but not how you're thinking about it, friction-wise, we are going to have air that's going to be converging around the city and rising. This rising air is going to cause heavy rainfall. Now, if we weren't in Milwaukee, that would be the end of this story, and we would have an increase in our rainfall over urban spaces and downwind. But because we're in Milwaukee, we have to keep in mind that we have a lake next to it. And as that lake is right next to, or Lake Michigan is right next to it, we have air that is going to fill the void and cause extra water to move through this sort of cycle and cause a re-intensification of rainfall. So this is sort of like a wicked problem, where we have both the presence of the city itself, the heat in itself, and this rainfall that's causing increased flooding, and we have wants of needing to have more urbanization because we have an increasing population. It's quite difficult to be able to decide what we want to do. Well, one way that we can adapt to these hazards, at least hydrologically speaking, is trying to add in greening strategies or green infrastructure or low impact developments or water sensitive design or sponge city policies. There's an entire paper that just says this is all the ways that you can say green infrastructure. I'm choosing greening strategies here and throughout the rest of this talk, but we're trying to move from a city that qualitatively looks like this and goes to a city that looks like this, where we have an increased amount of tree canopy, we have downspout disconnection, which is broadly moving water from an impervious surface onto something that's pervious, like a turf grass or a rain garden or a bioswale. We have increased amount of green roofs, and we have permeable pavements. So why do we want to do these things? Well, greening strategies can help us adapt really well to both hydrologic impacts as well as some of the heat impacts. In a study that was done in 2010, this is a really good representative study of what green roofs are able to do, where we have a rainfall impulse, we have an impervious surface that's going to be the amount of runoff that comes off an impervious area, and then we have how much runoff is coming from a green roof that was basically co-located with this rainfall, or with this impervious surface. And we can see that we have both a reduction in when our peak runoff is coming, so we're going to have a less flashy hydrologic signal, as well as we're going to have a reduced amount of runoff. And that is good when we're talking about cities themselves, because we're not going to have flood inundations, sewer water over, or sewer shed overflow, things that we don't want to have happening in our urban spaces. And at the same time, we can look at some of the other co-benefits. Trees, in a lot of different studies, have shown the ability to help reduce air temperatures when we look at them in single points or at the scale of parts. And each of these little dots, as it goes towards mean on this, is showing an air temperature reduction. But you can see there's quite a lot of variability in if that reduction is actually reduction, the magnitude of the reduction, and also the sort of mean is not really that confident in that reduction. So the problem with this is that what I've been talking about and outlining so far is that these have all been site-specific studies. We know how each of these greening interventions are going to function in like a single column of like, I know if I put one tree here, I should expect this much cooling in this vicinity. But, and then in the scientific literature, what we usually do and look at is, okay, because we have these site-specific studies, we're going to be able to go and scale this to the size of the city and have city-scale cooling, city-scale benefits to hydrology. But we actually don't really know if that is the case. So we need to be able to have the ability to look at both hydrologic and heat benefits commingling together within these sort of spaces to be able to get a better understanding of resiliency as the climate continues to change. So in my dissertation, I've worked through 4 main chapters. All of these chapters are going to be more of a amuse-bouche of what I did. So you're going to just have little bites of what happened. There's a lot of other stuff. We're going to avoid GIS as much as we can here, even though I spent a lot of time with GIS. So my research questions for my chapters are as follows. In chapter 2, we're going to be asking if there are water and energy changes that are important in greening strategies when we put them into a land surface model. I'll explain what a land surface model is in a little bit. In chapter 3, we're going to be looking at what are the effects of greening strategies at the scale of a city during rainfall and heat waves. We're then going to look in chapter 4 about how atmospheric processes and rainfall are affected by greening strategies. And then finally in chapter 5, we're going to see what changes we can expect when we start to implement these real-life management scenarios that greening strategies are focused and trying to be put into practice, and see what we can potentially expect to see happen. So we can jump straight into chapter 2. So first question is, why are we doing this, right? I kind of outlined a big problem, but what can we do in the hydrologic space? So in hydrologic models, we are either going to be modeling urban spaces as links and nodes, where we have water going into a little node and then it travels along a link, and it does not have, or this is going to be things like EPA swim or other tools as such. We could use really computationally intensive hydrodynamic models that resolve individual buildings that can give us flood inundation, but aren't going to be really useful for hydrologic purposes because they need to be ran over long scales, and this is more of an event-based model. Or, to shout out Voter and Lohi 2018, we can look at really detailed parcel-level scale models that have that model individual sites or even city blocks. But this again is going to have issues with with computational price, though they are very useful at site specifics. The other big problem that comes from this is that we've been looking at this slide through the lens of just hydrology. So we're ignoring any impacts that hydrology is going to have with the overlying atmosphere, such as changes in air temperatures and potentially changes to atmospheric circulations like precipitation. And as I've said many times, very computationally expensive. Now, the other side, the other tool that we currently have to be able to do this is we can use regional climate models. These are usually coarser, so instead of trying to do individual buildings or individual parcels, we're going to be doing sizes of 1 kilometer, 3 kilometer grid cells in the X and Y space. And they're going to be mostly focused, instead of on hydrology, on trying to get impacts of roughness and momentum and energy transfer. So they're trying to do a different thing, even though they're in a related space. There are 3 different flavors that we have in regional climate models to date. One of them is a slab model. It's the easiest to use. It has permeability and albedo changes, as well as increased friction, but it's effectively a flat piece of pavement. And this is currently the standard when we run our regional climate models and our global climate models. We have a single layer model where we are able to get an infinite canyon that has some radiation processes, as well as some changes in fluxes from our individual rooftops, our roadways, things that are important to urban spaces themselves. And then we have a multi-layer model that is going to be trying to parameterize turbulence in all of throughout all of the urban canyon, and have different buildings and tries to 3D represent buildings. It's very complicated and very, very computationally expensive. When I was stressing this, we were missing a big thing. Trees, grasses, green roofs, vegetation. The urban spaces and urban regional climate models ignore that for the most part. And we also don't have any really basic hydrology that is implemented into these. So there's no way of being able to pass water in between interfaces, which are inherent and critical within our urban spaces themselves. So in chapter 2, what we did is we said, why not merge the two? And I created a land surface model, which is the model in a regional climate model that models of the land surface. And we added in urban hydrology into that model itself. So we are able to represent urban eco-hydrologic interactions, such as urban trees and trees that overhang pavements, passing of water from an impervious surface to one that's pervious, permeable pavements, green roofs, and then we're also able to get at heterogeneity by having multiple land cover types within our grid cells. So instead of having a 3-kilometer grid cell that is going to be just one land cover type, we have a 3-kilometer grid cell that is made up of an individual distribution of different land covers. So you can have a building, a tree that overhangs pavement, a green roof, that's all mixed together and then fed back to the atmosphere. And then we can see what happens. To give a little bit more of an overview of what NOAA NPQ does, at its core, we add in a mosaicing scheme very close to someone who's on my committee, Dan Lee's version for a similar land surface scheme, where again, we have multiple land cover types all together, and then you'll note that we have these arrows. These arrows are representing the passing of information, in this case water, in between those different land covers. So, in terms of urban trees, we have 1 being an urban tree, and 2 being a tree that overhangs pavement. And tree that overhangs pavement is allowed to pull soil water from the land cover 1 and evapotranspire it, which is pretty simple, but hasn't been done before. And also adds in the ability to add in shading over these pavements, which is pretty critical when we start to think about the impacts that heat or green infrastructure can have on heat. And then for our urban to turf grass and permeable pavements transfers, those are just going to be passing water using a scaling factor that they move from an impervious surface to a pervious one. Because I have given a lot of talks on this, we're just going to get a little piece of what this is, and we're going to look at urban trees to show off how these seemingly small changes can make big impacts. So I'm going to be showing off 3 different simulations. One of them is a typical model, which is tree and pavement with no tree cover. Yes, that is a real tree. Thank you so much, Steve, for finding that years ago. It is my favorite photo I think I have that I used in my research. So this is how a typical model would work, and even the state-of-the-art mosaicing models without any ecohydrologic interfaces and changes. And it's always going to be denoted with this icon where we have 50% tree and 50% impervious surface. Then we have a parcel scale model that is going to be that same tree that got cut before it got cut. This was the before the tree, this is the after tree. Be nice to your neighbors, is what this is saying. Where we're going to have 15% is going to, of our volume that we're going to be looking at is regular impervious surface. 35% now has tree that overhangs the pavement, and then we keep the amount of tree the exact same. And then we have sort of an intermediate where we did a GIS analysis to determine that around 10% of tree cover overhangs the pavement to be able to look at this in suburban areas within the Milwaukee area. Now, this is our setup, and to be able to read the next plots, we're going to be looking at bar charts of seasonal water fluxes. So the blue colors are going to be runoff, so that's going to be water that would be potentially going to flooding. And the darker the color, the more likely it's going to be coming from a pavement, and the lighter the color is going to be coming from the vegetation. Greens are going to be evapotranspiration using the same sort of workaround where we have a large amount of, or a brighter color going from tree over yard and a darker color going to tree over pavement. And then to round out our hydrologic budget, we have deep drainage, which is the amount of water that's going to potentially go to groundwater recharge. I don't model groundwater explicitly, but we're just going to be calling that deep drainage. And then we have soil moisture storage, which is in this case always a deficit. So it's always going to be negative, and it's just a measure of how dry you are in relation to where you started at the burning season. This is an average, going to be shown as an average of 3 years. So to show off our big impacts, this is our no, this is our moderate, and this is our high. And we can see that we reduce the amount of runoff on average by around 80 millimeters, which is quite a lot of water to be infiltrating and saving. So the next question that comes from this is that where does that go? Well, an overwhelming majority in this sort of case is that it goes to evapotranspiration. So evapotranspiration is going to be helping cool the surrounding area because it's going to be taking energy from the sun, and instead of partitioning it into air temperature, it's going to be making water into a vapor, which is very useful when we start to think about adding in tree canopies. Then we also have deep drainage, which is being reduced in this case, which means we're just using more water for evapotranspiration, this enhanced amount of evapotranspiration. And then we also have soil moisture deficit increasing. So again, we just have more water going towards evapotranspiration because we have more tree canopy in this case that is being allowed into our model. Not shown here for time, but we did another set of simulations that kept the amount of tree canopy the same, and we just shifted it. And with that, we still saw a very similar signal. So it's not just the fact that we have more tree canopy, it's that we're moving this tree canopy and allowing this to have a more realistic physical representation within this model. So I also promised in this chapter to talk about energy changes. So we're going to think a little bit more about the energy cycle. I work really cleanly and in between a lot of different fields, as was talked about by Dan and Steve. So when we think of sensible heat, we're going to see this a couple of times. We're going to be thinking of air temperatures because that's going to be the energy that goes towards air temperature. And latent heat, we've already seen. That's just evapotranspiration by another medium and rescaled by 2 divisors. So in our typical simulation, this is the average day that I've averaged over many, many, many days to be able to get what the average and the variation is for our sensible heat and our latent heat. This is for our hydrologically aware parcel scale model, where we have a drastic reduction in the amount of sensible heat at the peak, as well as an increase in both variability and the amount of our latent heat fluxes. And because I have 3 advisors and I can't say no, we did this 56 times and over a different distribution of a lot of different parcel makeups. We were able to create and show that there is a relatively linear signal between these, where in this case at least we have a linear decrease in sensible heat and a linear increase in latent heat effectively. Though this is only when we're thinking about hydrology and energy without the overlying atmosphere. So that is where we end up with the simple story, and we get to go to more complicated and fun stuff starting next. So that was chapter 2, and then we move into chapter 3, where we're going to be talking about how these greening strategies are going to be affecting surface variables, so air temperature, humidities, and their biases within the Milwaukee area during heat waves and rainfall. We picked heat waves and rainfall because they're interesting, and I like them. So we have a way to be able to represent hydrologic processes at the scale now. Yay! So let's evaluate some of those changes. Before we go any further, I have to give an overview of what my favorite model in the world is. It's the Weather Research and Forecasting Model. It's a broad overview of how these models work. So we're going to start with large-scale atmospheric forcings. So think humidities and winds and temperatures, but not just at the surface where we see them on our iPhones or phones or look up on our weather apps, but throughout the entire atmosphere, going all the way up thousands and thousands of meters above the surface. And then we're going to pair that with detailed information about soil and vegetation and land cover and land makeup. And we're going to do a lot of really terrible processing and get them in Fortran and do some crazy stuff. And then we put them into the WRF model, which has different physics parameterizations or different ways to say this is what the physics are doing to work on radiative transfer. So sunlight coming from the sun and how it gets to the surface and bounces back through clouds. Cloud microphysics, aka the dark place where I don't go, but my friend Holly Mallinson loves to stay there, so we don't do that. A momentum and energy solver for being able to talk about how air is going to be moving across an entire region. And then, of course, land surface processes, because that's what we want. And then we get high resolution outputs. We want to make sure that we are going to know that we are changing just one knob in this WRF model to make these changes in land surface processes, and we're trying to see what these changes are throughout the entire atmospheric system. So sometimes it gets a little messy, and we are going to just have to be okay with that. So we're going to use the Weather Research and Forecasting model using this domain setup. I'm using ERA5, which is just a reanalysis, or like a fancy regional climate model, global climate model in this case, at my edges, and I have 2 domains. One of them is 9 kilometers, and then the interior domain is 3 kilometers. 3 kilometers is kind of special because we get to turn off some of the physics, and we get to have more fun with like convective rainfall and like the fun stuff in the summertime. We simulated 12 events, and we're going to be looking at them in Milwaukee. I'm going to be showing 2 different simulations. I actually did 3, but again, I'm only able to give you an almost boosh. So those 2 simulations are going to be a typical model, which is going to be that flat piece of pavement, and then one that uses NOAA NP-Hue, which will be denoted as Hue from here on. Our typical model is going to be the out-of-the-box WRF urban model. That is that 0th order single layer, or 0th order flat piece of pavement model that we talked about in the first chapter. And it's used in so many applications, even at this really fine scale. This is the land cover distribution that we have in the Milwaukee area that we're using. And again, it's not going to be able to get at the heterogeneity itself. This is our distributions that we were able to derive for the Hue model. So you'll note just at the start that we have quite a bit of heterogeneity within our land covers themselves. So, which is great. We love that. And so we're going to just have increases coming from that, but we're trying to really tease out, are there other changes that are coming from this increase in urban hydrology? So to start off, let's look at 2-meter air temperatures and sensible heat fluxes. This is the average of the 2-meter air temperatures that were simulated by the typical model. And you'll note that there is a sharp gradient between what I'm calling peri-urban areas, which are these areas that are in this region but do not have a dominant urban land cover type, and more urbanized areas. Then we also have suburban areas, which are more of this interior, and then we have the heavily urbanized or downtown region. And we can also look at our sensible heat fluxes, which are shown in our diurnal patterns, where again, that's the amount of energy that is going to be going towards this air temperature in these simulations. Then we can look at the Hue model. If we pay attention just to the peri-urban spaces, we don't have that much of a difference in our air temperatures, and we have a slight increase in the amount of sensible heat flux. That is maybe a red flag, but on initial gut check, but it shouldn't be, because we're actually able to represent those tiny little urban areas that are in this peri-urban space now. So we're getting a better representation of urban spaces themselves. In suburban areas, we see where Hue starts to really shine in terms of having a reduced amount of sensible heat fluxes. And then in our heavily urbanized areas, we reduce the amount of sensible heat flux that's partitioned in Hue by almost 200 watts per meter squared at the peak, which is quite a lot. So this is going to be a main driving reason why we have a decrease of almost 1.5 degrees Celsius across the entire domain. We can do the same thing with specific humidity, which is just a way to measure how much humidity is in the air. It's similar to relative humidity, but it's not a percentage, it's just a value. One thing to note about the typical model that you can see is that there is no latent heat flux in the suburban and peri-urban or suburban and heavily urbanized areas. That's because there's no vegetation, because this is a flat piece of pavement. It's effectively going and laying out in a parking lot and being like, I love it here. And that's what this model is currently doing. So we have this drastic jump that occurs from peri-urban spaces into urban spaces, which is just not physical, right? We have this nice gradient that probably is not real. If we look at the Hue model, though, we start to see a more realistic gradient occur, and we are going to go from a more humid peri-urban space to a less humid, heavily urbanized space, but the less humid urbanized space is a more realistic value. So as we move on, we have less and less energy being partitioned to latent heat fluxes, but that should be happening because there's not a lot of vegetation in heavily urbanized areas. Now, in addition to this, in this project, we really wanted to be able to look at changes in latent and sensible heat fluxes, but those are basically impossible to measure accurately in urban spaces. My Encore Desai on my committee would be able to tell you more about that than me. So we have to use proxies like surface humidity and surface air temperatures to be able to do that. So we ended up being able to pull a relatively dense weather network within the Milwaukee area to be able to look and see what are the biases and like skill score metrics in our different simulation types. So for our 2 meter air temperatures, we have, for the typical model, we have a relatively skillful scattergram shown here with a pretty good Pearson's R squared value, but our typical biases are showing that we have a very, very hot bias that's occurring throughout the entire domain. So it's probably not the best thing to be using. But when we look at the Hue model, we have a correction of this bias. We have much more believable heterogeneity within our mean biases, and we have an almost identical Pearson's R squared score. So this we take as a win in this case. Yes. When we look at surface humidity, we can do a very similar thing. We obviously have a dry bias because there was a sharp gradient that occurred in our maps that we just saw. And humidity is much harder to be able to measure or to be able to predict in models compared to air temperature because of the processes with them. So we have a reduced Pearson's R just in general. But we get a marked increase in the skill of our model when we use Hue. So not only are we saying that the surface heterogeneity is helping, but also likely when we compare this to the mosaic or the third simulation type that I'm not showing, we do get a better representation still. So this is saying that urban hydrology does affect surface meteorology, which is very cool. That's it for chapter 3, and now we're moving into chapter 4 and chapter 5. Chapter 4 is an examination of more atmospheric processes and rainfall processes. So far in this presentation, I have just been talking about this bit of the atmosphere, right? But really, there's a whole other bit of the atmosphere that we just kind of are like, oh my God, there's smoke because a wildfire happened miles away. Oh no. That's usually when people start to like recognize that. But that's also an important part for our like day-to-day life. So understanding if there are changes in that can help us tease out changes in rainfall. We're using the exact same setup, exact same simulations, but instead of just looking at heat waves and rainfall events, we're only going to be looking at convective rainfall events. We're going to show the same 2 simulations types, one that's typical and one that's using Hue. So same basically everything, just wanted to make sure everyone's on the same page. We now have to talk about boundary layer meteorology, and it's a very tricky bit, so I'm going to try to walk us through this in a very clean way. One way that we can get measurements of the boundary layer without having to use any fancy techniques is using airplanes that are taking off and landing in the Milwaukee airport. So through the use of a lot of magic that we won't get into, and I lost my mind over 2 months figuring out how to do it correctly, we can create a profile of the average afternoons that were derived from airplanes that were taking off and landing within the Milwaukee area itself, shown by this black line. This is potential temperature, which for all intents and purposes is a temperature, okay? It's a slightly different thing that I had to put on here to make my heart happy, but it's a temperature to everyone else. Cool. But because we're starting to look at not just the surface, we're looking at the atmosphere, we have to do a little bit more careful separation. So we need to look at what we call lake breeze conditions, which I will get into in this next clip. But you should note that there are 2 different, we can also have this different like profile that comes out. In traditional land surface conditions, we have a air mass that is going to be moving from the west to the east, so from Milwaukee towards Lake Michigan. That's going to be the traditional day-to-day. But on very special days, we end up having this reversal. That's called a lake breeze. where air in the boundary layer is going to be coming from Lake Michigan and moving to our urbanized space. So we have to be able to differentiate these because we have a very different air temperature profile that pops out, so we need to treat them differently. So, black lines are our observations from our airplane measurements that we were able to use. The red line is the typical model, and the green line is the HUE model. From this, in non-Lake Breeze times, HUE is doing worse, but that is because we have more realistic surface humidity and more realistic cooler air temperatures at the surface that are feeding back into the upper or into the boundary layer atmosphere. But we get a better specific humidity profile. We are closer to observations, and we're matching it in the lowest 200 meters above ground level, which is great. So that is a win. When we start to look at lake breeze events, we are getting a better representation of lake breezes from our HUE model, and specifically in temperatures. And we have uncovered an interesting bias that has occurred within our regional model, where we have a reduced amount of specific humidity, so we have less humidity during lake breeze events, even though there should be more humidity. One of the reasons we came up with this is that the parameterization that we were using for our Lake Michigan temperatures was using really coarse data that we then corrected for the fourth chapter. So we're using something different, and those temperatures were likely wrong and then causing this issue compared to our observations. But it's hard to be able to dial this down because there are millions of parameters that we have to kind of like think through and decide what could be happening. Overall, from this analysis that we were able to show, that HUE is going to be cooler and more moist over the Milwaukee area, basically always, and sometimes, or in a majority of the times, that's relatively a good thing compared to our observations. So that's a great win. Another thing that I've been promising is talking about rainfall, so we can also talk about rainfall. This is another data product that's called AORC, which is effectively radar plus a couple of bells and whistles. But it's gridded, and we've taken the largest events that we have, and we've put them all together and averaged them together, as well as provided the Milwaukee Metropolitan Sewerage District has provided us 21 different rain gauge stations across all of Milwaukee to be able to get to be able to also analyze. So we have ground truth point observations and pretty much truth gridded observations. This kind of wet area in the middle is that urban rainfall intensification fingerprint that I was talking about at the beginning of my presentation. So this is a real thing that we need to be able to represent within our models. This is the representation of the typical model. We can see that in the exo parts of our urban spaces, we have an overprediction of rainfall, but within our very critical portion of the urban rainfall intensification, we are not getting the rainfall story correct at all on average. And then in HUE, we're actually doing way better, which is awesome. We get this urban rainfall intensification process likely better, and because we have the increased amount of, or we get a better meeting of our rainfall totals from AORC as well as the individual MMSD rain gauges. You'll note though that still on these exo-urban spaces, we are over predicting rainfall. This just points to the idea of we are changing one thing in a very complicated model, and it's not going to be a panacea for all of our issues. So we have to be able to be like, okay, focus on what we want to. There are other issues that we will have to fix as we move forward. Now, we can dig a little bit deeper into why we're doing better by introducing another set of data. So we're going to be looking at maps of what we call integrated water vapor transport, which is just effectively how much water is moving to different locations in the lower atmosphere. If we look at the typical model during 1 hour ahead of our maximum rainfall totals, we don't see a lot of integrated water vapor transport from Milwaukee or from Lake Michigan. But when we look at our HUE model, these small changes in gradients of air temperature and humidity are cascading to cause large changes in the amount of integrated water vapor transport, so we have more water that's available to be whisked away to the upper atmosphere. We know that it's going to the upper atmosphere because we can look at another thing, which is the low-level convergence. So blue in this case is going to be saying we're moving up, and red is going to be saying we're moving down because of how I've addressed the negative sign as Anne looked up at the ceiling. So the big thing that's occurring, if we see in the typical model, we have a large area of air that's moving down ahead of our rainfall or our intense rainfall. But in our Q model, we have a large area of air that's moving up. So we have this sort of counterfactual of more air is going to be moving up and having that rainfall intensification process that I described at the beginning of this presentation. And when we look at the additional rainfall or the maximum amount of rainfall that fell, we see that there's quite a drastic difference, and especially in and over the Milwaukee urban area. So these all interrelate together are pointing towards small changes at the surface can cascade to make bigger changes in the atmosphere, which is pretty fun. I think it's cool. So that was chapter 4, and now we can start talking about chapter 5. Management scenarios, are they great? Are they not? Who knows? So let's click one more time. Great. So as a reminder, this is what Milwaukee's green infrastructure or greening strategies are. They want to increase tree canopy, they want to add downspout disconnection, they want to add green roofs, and they want to add permeable pavements. So we are going to be able to now, using the tool that we've developed and validated across 2 different other studies, how there's joint changes in hydrology and heat at city scale. To be able to do this, we need to have an idea of where we should be putting these things, and that is a really tricky problem. We're very lucky that the Milwaukee Metropolitan Sewage District gave us an in-house metric to help us determine where to put greening that is ranked on a scale of 1 to 5, which takes into account, is it hydrologically good to put in some sort of green infrastructure, as well as it hydraulically feasible to put this? What are the potential ecosystem services that we could be getting? And what are the socioeconomic considerations that we should be considering when we are doing this? So 5 is going to be most grading. 1 probably shouldn't be getting as much grading. And we can take this and do a spatial average to get a map that helps us prioritize within our WRF model where we should be grading. So we use this map, a lot of math, and then targets that are shown here to be able to get our greening maps themselves, and then we put them into our WRF model that we ran from the 1st of June to the 1st of October 2022, and we tested to see what are the changes in hydrology and heat. The 100% greening is quite a lot of greening. So we're adding in 50 square kilometers of extra tree cover, we're adding in a lot of new green rooms, we're fully disconnecting all single family parcels, which means if you have a family, a single family home, you just remove all of the water that goes to the stormwater system, and you put it on the turf grass first. It's a lot of very fancy language for something that's pretty simple. And then we also wanted to look at sort of a counterfactual or like an extreme. So what we did is we doubled everything and then added some. So tried to go as much as possible to see what could happen. And this is all going to be relative to current conditions, which is very similar to what we were seeing in chapters 3 and 4. When we look at this over an entire growing season, we can first examine what the amount of runoff is from our 100% greening and our extreme greening cases. The average amount of surface runoff from 100% greening is 146 millimeters, which is a lot-ish. There's a lot of water that is coming from our downtown urban area and not a lot from our suburban or peri-urban spaces. And we have a giant or a large reduction when we look at this extreme greening case. If we look at this delta, this as a delta relative to our baseline, we can get a much better impression of how much reduction we actually are getting. So we have a change in surface runoff of around 30 millimeters. A lot of that is coming from the downtown region. It's much more widespread in the extreme greening case. So we're not just getting reduction in the downtown area, we're getting it into our suburban and peri-urban spaces. We can also look at changes in evapotranspiration. So increases in evapotranspiration are best in greening, or the extreme greening case, okay in the 100% greening case. And then in deep drainage, we have a weird looking map that's coming out. And that's because we only prioritize locations for permeable pavements in places that they would actually possibly be able to go, which is not across the entire Milwaukee area, but instead in urbanized spaces, or like heavily urban spaces. So those are just the pixels that ended up having a heavily urbanized space. Another thing that we can look at, in addition to these hydrologic budget bits, is changes in rainfall. So this is the baseline rainfall case across our entire seasonal rainfall scale. And we have quite a sharp gradient that occurs where we don't have a lot of rainfall in the south, and we have a lot of rainfall in the north. And we have that fingerprint that still comes up with our urban rainfall intensification. These are the 100% greening and the extreme greening cases, but this is not very useful because these colors are very similar to one another. So we can now, again, look at this change in extreme greening, or this relative to baseline delta. And we can see that there is quite a lot of difference that's coming from this change in rainfall, especially in our heavily urbanized spaces. But that leads us to the question of what's driving changes in our runoff signal. Is it the change in rainfall, or is it our hydrologic implementations? That becomes a tricky question. That way I tackled that is using simple linear regression. You can learn a lot from a line. So this is a scattergram that we're going to walk through. Each of these small dots is a single pixel, and its relative change between 100% greening and the baseline itself, or the extreme greening for change in surface, and then the change in surface runoff, and then we have change in rainfall on the y-axis. You'll note that it's kind of hard to be able to compare these one-to-one because the y-axes are different and the x-axes are different because each of these has its own change in surface runoff and change in rainfall. So instead, what we're going to be focusing on is these lines of best fit. The slope is going to be showing us the sensitivity to rainfall, so changes in rainfall are going to describe how sensitive we are to an increase or decrease in rainfall. We're more sensitive to changes in rainfall in our extreme greening, and we're pretty sensitive to rainfall for 100% greening. I'm saying pretty sensitive to rainfall because in our simulations that I'm not showing, because there's 18 of them, 18 different cases that we did effectively, the slope is 0.66. So we are going from something that isn't very sensitive to something that's pretty sensitive to something that's extremely sensitive. Our intercept is sort of the number that we're looking for. It's the amount of runoff that we are going to be expecting change given no change in rainfall. So we can see that we have about double the amount of runoff reduction expected from our extreme greening, though we have compared to our 100% greening. And sort of interestingly and counterfactually, we're looking at also for a change in this linear relationship, this r-squared value. We actually end up wanting a worse r-squared value because that means that we are making a non-linear system. So hydrology should be mattering more, not just the change in rainfall itself. I also promised during this to look at heat, so we're going to briefly look at some heat results. I think they're very fun. So this is the number of days that we are going to be above 32 degrees Celsius or 90 degrees Fahrenheit for us that live in freedom units. This is important for the state climatology board here in Wisconsin, that's just down the hall. So we're using this as our metric here. And this is the change in days that reached 32 degrees Celsius in 100% greening, and this is the change in extreme greening. So we can see that there is a reduction even when we have this 100% greening, and we have a stronger amount of reduction in the extreme greening case, especially in sort of some of these downtown pixels. We can also look and see at the changes in the air temperatures compared to the baseline, and we see that extreme greening is causing, again, a strong signal of this reduced air temperature. But interestingly, if we analyze not just the air temperature changes, but instead look at the heat index, which is the feels-like temperature that you get on your phone, we don't see as big of a difference that occurs, especially in the afternoon. This is a diurnal pattern of this heat index change relative to baseline. And we are hovering around 0.1 degrees Celsius changes in our heat index for 100% greening and only 0.2. So we're effectively doubling compared to something around tripling or quadrupling with air temperature itself. This points to the idea that we may be going the opposite way of adding too much humidity to the atmosphere and increasing our heat stress in some cases. So that's something that we're going to be looking at more when we do more simulations, because this project is still going. So that was my 5th chapter. What did we find in this work? Well, we found that small changes in land cover associated with greening strategies do have impacts on season-long hydrologic fluxes and energy fluxes. That the inclusion of greening strategies can create closer to observations in our surface meteorology variables. We have a better representation of intrinsically important surface or atmospheric processes that are occurring over cities, both in ahead of rainfall times and rainfall times, and that we are starting to be able to identify trade-offs that may be occurring with our management strategies, right? If we increase the amount of greening, we may be getting a really good hydrologic signal in terms of runoff reduction, but that could also be causing problems now with our heat reduction, and we could be making heat actually worse due to experiential temperature for humans. So we're able to start now teasing across these co-benefits, so to speak. The key takeaways from my projects are that for the scientific community, urban hydrology is critical, and we should really be paying more attention to it in atmospheric sciences as a whole. This is a young field in terms of atmospheric sciences. Urban spaces have only been in land surface models since 2005-ish, really. It used to just be a rock. So we got a lot of work to do, and we need more people sort of like me that are doing both at the same time to be able to get things really working. And then a lot of my work has been working with city decision makers, and a big key takeaway from all of my work is showing that your greening strategies aren't just going to be changing local hydrology, but they're also going to have feedbacks at city scale with heat and potentially atmospheric work. So we need to have these co-benefits clearly outlined in work moving forward. I would like to take a second to thank my research committee, my doctoral committee, the Hydroclimate Extremes Research Group, the Hydroecology Lab Group, the Water Resources Engineering Group, all of my funding, the NCAR supercomputing systems that I have used so much. I once was running more than 50% of the available nodes on NCAR, that was a time. It was so fun. The Milwaukee Metropolitan Sewerage District for their support. And then I also wouldn't be here without my friends Sam Hartke, Holly Mallinson, Ashley Spursky, Zoe Rosen, who is wearing the jumpsuit with me, Enrique Goulart, Matt Mishk, Ben Fitzgerald, Jack Williams, and Hannah Curtis. Those should be flipped, but whatever. And my family for helping me out and supporting me through this, because I had to relearn how to walk during this PhD. So, yeah, the research was fun, relearning how to walk was the challenge. We're now on to the next chapter of what I'm doing, and I'm ready to take questions. Thank you, everyone, for your attention. For those of you who are asking questions, you have chocolates, so because I know I was going to be talking a lot. Okay, questions?
I have 2 questions, but I'll hold on the chocolate, or I'll defer them to someone else that might want them.
Cool.
But I like the idea. Very nice presentation, thank you. You explained things very well.
Thank you.
Which, if I can understand it, then it's explained very well. One smaller question about the last piece with the heat index.
Yes.
Is that mostly just temperature and temperature days? Because public health has other like comfort indices which have temperature and humidity.
Yes.
Might you get some slightly different results if you're looking at something like that? So now we're
Yes.
talking about human health, could be
Yeah.
animal, but mostly human health.
Yes, so there is a lot of work in urban spaces that are showing that there is this change in change in outcome depending on the change in, or the metric that you're using. So we were just using the basic one here, which is the feels like temperature, which is just a linear regression with relative humidity. But future
So it does
work-
have humidity in it.
It does have humidity in it. What I will be doing moving forward is using the wet globe bulb temperature, which is a little bit more robust, or the UTCI, if I can figure out how to calculate it from the WRF output. There's a variable that I need to figure out how to get at. But there is humidity in this, but the answer could change a little bit depending on which metric we use.
Yeah, great.
Yeah.
And then my other question was, so most urban areas and growing urban areas are coastal, including Milwaukee, but not all.
Yeah.
So presumably, having that coastal has some effect. You know, what's critical, or what change is critical for some urban area that's, I don't know, more inland or away from large bodies of water?
For what aspect?
Yeah, so how would you expect some of these things to change? How dominant is it? I think we all probably get that. Clearly, it's very different if the lake's not there versus there.
Yes.
Right? So you don't, so it's moisture, it's reversal, I mean, it's
Yeah.
just a totally different system,
It is a
right?
totally different
So would what you're learning here be applicable for a city that doesn't have these mechanisms, or do you back up a lot?
Yeah, I think that some of the through lines of this work are applicable in terms of, like, we would see a temperature reduction by adding in greening,
Yeah.
but the amount of temperature reduction is going to be very different, likely because of this change in circulation that happens with coastal areas. That's already going to be reducing our temperature a lot, so we actually might see more temperature reduction. It's also going to be really a factor of the underlying climate of where your city is located. So places like Phoenix, you're going to see a big temperature reduction, and then places like Baltimore, you might not see a temperature reduction at all because it's already so humid. Adding more water to the air is not going to help you. So, yeah.
Thank you.
You're welcome. Oh, okay. Yeah, Mer.
I don't understand.
Are you sure? I bought these for people. Take the chocolates.
I'll take one, and then I'll take the highest bidder, so.
Lulu, do you want a chocolate? Yagmer first, though.
So my question is kind of parallel to what Paul was asking. What is the transferability of your work temporally and spatially? Because you worked on some committed scale events. How can you apply this work to longer seasons, years, and other places? What is the transferability? Can you talk
Yeah,
about that?
of course. So this, like, the conclusions of my work are broadly that we could say there's going to be a temperature reduction, but we need to do more. The model that I developed during this work is transferable anywhere in the world. And that's what we're kind of doing for my postdoc, working with Courtney, who's sitting right next to you, on developing pipelines to be able to do that at different spatial and temporal study, or at different scales. There's still a lot of work to be done still in Milwaukee for the amount of climate that we're doing, like climate changes, or trying to do with climatology, not climate changes, climatology. That's going to need more years to be able to get at, but that's something that we are doing. So I guess stay tuned. Yeah.
Thank you.
Yes. Lulu.
I also have two questions.
Okay.
Because I have two chapters.
Yeah.
Okay, sure. Two chocolates.
First question, chapter 2. I know that we didn't do this work, but does spatial configuration of the elements or the elements matter? I know you have the components,
Yeah.
proportions, but not necessarily where.
Yeah.
It's an opinion question.
So at a more local scale, yes. At the scale that we're doing it, as long as you're with like your intragrid and you just have those proportions, no. But if we went down to really, really tiny, or like street scale simulations, it would really matter a lot. Does that make sense?
Yeah.
Yeah.
And on chapter 4,
Okay.
so you change the atmosphere because of moisture.
Mhm. Yes.
Are you able to quantify the contributions of atmospheric changes? Is it more moisture?
Mhm.
Is it more?
So in this specific case, because we had a reduction in temperature and a drastic increase in humidity, we would be able to say that it is in most of the changes that we're seeing are due to the humidity changes, not necessarily the temperature changes, because increases in humidity will increase the amount of instability, so make air more buoyant, and temperature changes in the decrease make it more stable. So there's an offset that's happening there. To be able to actually quantify that, we would need to go further into boundary layer meteorology's plethora of metrics on buoyancy to be able to get that, but that is something that we could do, yes. Yeah. Here are your 2 chocolates. Pass those. Great. Cool. Other questions? Ian?
2 questions.
Great.
First one with regards to with regards to the lake freeze, it's strongly influenced by the temperature gradient between the lake surface and the air temperature.
Yeah.
Do you foresee a decrease in air temperature over Milwaukee impacting how deep the lake freeze penetrates further inland, and what are the ramifications for that with regards to agriculture west of Milwaukee?
That's a good question. I haven't thought about, to answer the one that I thought about, yes, there is going to be a difference that occurs with how deep our lake breeze is going in. We were actually able to see that in some of these simulations where lake breeze events were not going as far into Milwaukee or further because of this change in temperature gradient. That likely is going to be even more enhanced under climate change, with changes occurring in our sea surface temperatures are going to be increasing by quite a lot, and then we're going to have sort of a different or a similar to lower air temperature in the city with this greening strategy, so we might actually be shutting off that knob. So that could be pretty detrimental if we are thinking in like the agricultural space, if they're dependent upon that cooling to be able to reduce the amount of irrigation that they can be using, as well as if there is like convective initiation that they want to be using for like rain-fed crops, that's probably going to be something that they should be worried about, but that's like 7 steps down the line. And figuring out how to say that to farmers is going to be harder than what I just started off.
And my second question was, these events that you looked at are mostly convective.
Yes.
I'm curious on when you are to expand this to a more long-term study. Do you foresee there being, as there's enhancements in moisture at the surface, do you think there's going to be greater amounts of low-level stratus forms, not even just precipitation, but just cloud cover that further leads back into a decrease in temperature?
Yeah, that's an interesting question. It could be. A lot of the stuff that we had been looking at was more of like the sort of sexy stuff of the convective rainfall, trying to get like extremes coming out, but I hadn't really thought about that aspect of an increased amount of cloudiness causing this sort of feedback loop. I did have to handle an issue with that in the model that was not my fault, but I had to fix in February because it was snowing in July, which is fun. But that could be a thing that happens, and I guess I'll just have to keep my eye out for it as I move forward, because I hadn't really thought about that. Cool. Chocolates? One?
Okay.
Okay. Yes, Jack?
So you talked a little bit about the many simulations that you ran over different aspects of greening. I'm curious if you considered any non-green climate resiliency approaches that cities could take, whether the sort of current sexy of New York's congestion pricing, decreasing the amount of cars and thus running in the urban areas, or other strategies like reduce albedo.
Yeah, so I did not run any of those. I do know of a lot of studies that look at what we call like cool routes, where they basically go out with a can of paint and then they just paint everything that they can white.
Yeah.
Which does have an impact in reducing the surface temperature and then changes air temperatures. But there's a consequence of that, as with everything, is that it actually increases the amount of ozone and ozone coupling that occurs in the near atmosphere and can cause worse outcomes for people with asthma. That's been shown in the LA area specifically because of NOx emissions. So all of these I think a big part of the work that I did was showing off that there are good things that can come from these management decisions, but there are things that we should be aware of because there are going to be trade-offs. It's not just going to be a greenwashing sort of thing of everything's great. There are things that we should also be wary of when we make these large-scale decisions. Other questions? Yes.
In these like Milwaukee area and in the region we are living in, I've seen like most of the transport of moisture is from west to east, right?
Mhm.
And the lake is on the downstream.
Yeah.
Of the wind.
Yes.
So what will happen if the land breeze and the direction of moisture is same?
Is
Like,
the same.
Part of it.
Yeah, so in like cities like Seattle and San Francisco and I'm trying to think of, or like Amsterdam. So things that happen there, this like urban rainfall intensification is not necessarily happening over the area itself, it actually is happening downwind. So you still get this urban rainfall intensification, but it then is just transported away and causes a more rainy, like plume effectively, just outside of the city and goes until it runs out of moisture. Yes?
Thinking to chapter 4 and effects, going back to the atmosphere, you showed changes in the boundary layer. Did you look at anything above the boundary layer?
No, I didn't. I love that energy of that question, and it's just simply not my business, Holly. No, there could be changes, but what we would need to do is we would need to use these simulations from like chapter 5 to be able to tease those out because it gets even more noisy as we move into the upper atmosphere outside of the boundary layer. Jack, another question.
I didn't get my chocolate.
Oh, okay. pass these chocolates back. One to Jack. There you go, Shar.
I just want to let everyone know that there are about 60 people online. And Aaron, they've been giving you kudos. I don't think they've asked any questions, but just want to, make sure that there are no questions that have come in from online. See if there are any more in the room. No, so there's still
Sadie.
4 more. Okay.
You talked a lot about rain, which makes sense because you're talking about the summer. And I don't have an atmospheric background, but like, how does your model, like, the changes that you're saying, how would they at all affect snowfall and how that changes?
It's a really good question. So it would be almost opposite of, it would be almost no change or opposite change. So if you were having snow when you were having our greening being in effect, so like in Milwaukee, like middle of October, we could still get some snow, and you would have the leaves on trees and this like reduction in air temperature, you would have potentially more snow that would occur or almost no change in the snow that was occurring because once the leaves are off, you're not gonna have much of a change. And when air temperatures goes down, the amount of water that the atmosphere can hold also goes down. So you're not going to see as drastic an increase in the amount of moisture that's available to be recirculating. But to be able to get those answers for that, we would need to, again, go to Holly's question, do longer term simulations, which is what we're doing soon, to be able to tease those things out. Okay, more questions. Oh God, okay. Courtney, and then we'll go back to Ian.
So urban areas are typically pretty dynamic, especially in peri-urban, also in the dense downtown.
Yes.
I was wondering how sensitive, if you have any indication of the change in buildings is, and that might come when looking at things over time. But if, for example, a building were torn down, or if they put up like a bigger high-rise, how sensitive is the model?
That's
to those sorts of things?
a very good question. I didn't address it in my work, but in studies that have been coming out from Rice or Texas, somewhere in Texas, I should know more about Texas, I guess. There was a study that was in Nature that showed that the amount of compactness and the amount of high rise in your city itself causes feedbacks to cause more intense rainfall. So if we in Madison or Milwaukee said, okay, let's add more high rises, we would actually see an intensification of this rainfall feedback. So that's also something to be thought about in case of management scenarios. Or if we went to like what Amsterdam does of like everything's like only 4 stories and really flat, you would get less of that. So this is a really tricky and complex problem of the interface between all of these bits can cause a myriad of changes. Yes?
Yeah, I have a lot of questions.
Yeah.
You can cut me off whenever.
Sure, go ahead.
We'll invite you to the closed door
Yeah,
session.
Perfect. The phenomenon we're seeing here kind of reminds me of, I think a term they use for sub-Saharan Africa. It's a green ocean. You're introducing a lot of moisture almost akin to a body of water.
Yep.
You're overwhelming water.
Yeah.
Do you think that when you green up Milwaukee, that introduces a buoyancy gradient between the areas north and south of Milwaukee such that you're redistributing rainfall to the north and south of Milwaukee? And then a follow-on to that would be more philosophically, if you're incorporating these sort of greening initiatives, do you think it should be a requirement to involve the surrounding municipalities when you incorporate these?
Yeah. So I'll start with the easier question, which is the buoyancy gradient one. Yes, I would say, so like in the early parts of the study, that chapters 3 and 4, we would be looking out across our entire like domain. We were able to clearly see that there were changes in our rainfall that were occurring in the Milwaukee area, but that was being shifted upwards or downwards or to the west. Specifically, like there's a lot that's happening in this bit for some reason that was just like seemed to be a magnet of where rainfall, the intense rainfall ended up being what we had in urban greening. So there is a change in buoyancy that is kind of driving this, but that is more of an atmospheric heat question. To the management question that you asked, you know, I think that yes, but doing that is going to be really tricky. So an example of this is the Milwaukee Metropolitan Sewerage District. This is like the part that isn't part of the Milwaukee Metropolitan Sewerage District. They're going to be seeing benefit from whatever is happening in Milwaukee, especially over the long term in terms of their temperature changes. But they don't like talking to each other, and they are actually quite adversarial sometimes. So trying to like work and do that requires not only like the work that I do, but also working with public policy and like social scientists to try to get everyone at the table and create something that everyone will be happy with, and not just this is what we're doing and you're gonna have to deal with it, which seems to be what a lot of things are these days. So, yeah. Other questions? Hi, Holly.
Time to get a couple things. When you mentioned intense rainfall, you're talking about the total amount of rain, correct?
I'm also talking about the like millimeters per hour as well.
Okay, that's fine.
We were able to also tease out that there is a change in the distributions of, we reduce the intensity of the extremes, but we also increase the amount of like drizzly. So we kind of shift our probability distribution a little bit. Which is good. Yeah. Love to be ahead of a question. Okay, other questions? Yes, Mary.
Kind of building on the Paula's question in terms of like sensibility, and you also mentioned like applicability to this to other places. We know Milwaukee and like other kind of middle and large cities looking to grow and expand and like urban sprawl. So I'm curious about your thoughts on, because like you described this format as a downtown, that's suburban, peri-urban, so kind of like a target.
Yeah, the bullseye.
Like multiple, exactly, bullseye. So with urban sprawl and kind of seeing that being extended, I'm curious about your thoughts of if you think this would apply and work in the same way, what other things would need to be considered and added
So
to that.
if we just go slightly south to Chicago, right? Chicago has a downtown center, but also has a lot of smaller like downtown built up areas, right? So you would have to sort of do an analysis like this where we do downtown suburban, peri-urban, but also do in smaller targets as well to be able to try to derive what those smaller targets are trying to feed back into the larger ones. It would become very crazy but fun. Yes, of course. Any other questions?
Well, I think that we have more questions for you that we'll reserve maybe for
Yeah.
the next part, but
Fair
I
enough.
think I want to make sure that we just give you a round of applause.
Thank you.
This was far more than the mini courses
Yes.
that you were promising.
Yeah.
Really nice
Almost
job.
boosh, yeah.
So please join us at
Let's do 12.
12.
Yeah.
12, and also later this afternoon, I think that we'll probably find our way over to the terrace.
Yes. Around 2.